Hello everyone, my name is Dejo Falk and I am here to present about image quality assessment. A little bit about me first. I graduated from George Mason with my bachelor's degree in 2022, ma- with my major being information technology. I concentrated on databases and programming while in my undergrad, mainly trying to focus on software engineering. I am now currently into my last semester in the Applied Information Technology program, concentrating in machine learning engineering, with taking classes like applied machine learning. I have mainly focused on looking at computer vision models and working with LLMs through my current work in the federal government. This project gives me a great opportunity to broaden my understanding within the computer vision field because image quality matters so much with how to pick datasets as well as implementing these datasets into computer vision models. So with this, I will now be introducing the paper that has started my own research. The paper that I will be talking about is Deep Neural Networks for No Reference and Full Reference Image Quality Assessment. This paper was published in the IEEE Journal, Volume 27, and every author in this paper has written either about image quality assessment or machine learning, particularly deep learning models. So they all are very experienced and have a wealth of knowledge on this subject. While researching this field, I really found a lot of papers and journals about this field. It seems that with computer vision becoming such a bigger topic within machine learning, image quality is also becoming more prevalent as well. A lot of papers that came out after this paper use this one as a reference for their research topic, which shows how influential this paper has been on this subject. This paper does go very in depth on this subject, so I want to give a brief overview of the core concepts that will be talked about in this paper before detailing the results of the paper. So I want to give some background knowledge on some of the key things that are within this paper and the field in general, starting with deep neural networks. As you can see with the picture on the right, the main thing about deep neural networks is that they have more hidden layers within the network. As you can see in this photo, it has three hidden layers, one input layer, and also one output layer. The depth and how many nodes that are within a network can change, but with deep neural networks, there are hidden layers that can be added or deleted to help solve the problem. These networks are based off the structure and functioning of the human brain and are designed to learn and represent complex patterns in relationships and data. The lines that link the nodes are weighted, and when the network is trained, the connections are changed during the training to produce a better output in the output layer. Finally, with these neural networks, the layers are fed forward from the input layer through the hidden layers and then land in the output layer. The layers are trained through backpropagation, which is a method that performs a backwards pass to adjust the network's parameters. So it goes through from the input layer, moving to the output layer, and as it goes in between each layer, it is recorrecting, backpropagating that line with the weight to make the best weight for the output. Before this project, I hadn't really learned much about image quality assessment. Like I said, I knew what a good image and what a bad image was on this particular computer vision model that I was using. But that can of course change on what you're trying to accomplish with your computer vision model. So image quality assessment is a very big thing that I want to learn more about. So when a human looks at an image, you can most of the time tell if the image has been altered or changed. This is subject image assessment, and this is the main way that image assessment has been done for a while. While looking into this field, I have found out mainly from a paper called Active Sampling for Subjective Image Quality Assessment that subjective image quality assessment is the main reliable and most accurate way of analyzing images. But with this comes a lot of time and a lot of people to be able to look at images. So if there was a way to get a computer to do this, it would save a lot of time and less planning for the subjective image quality assessment. The big thing about this method is that it does consider human perception. That is a big thing that we're trying to get computer vision models to do now. So we're starting at the human and trying to work our way to make the computer eventually become a human while looking at these images. Usually with this method, it is done with mean opinion score, which is when a group of human evaluators rates an image on a scale, and you take the mean of the group ratings. The other main way of doing image quality assessment is objective image quality assessment, which is using computer algorithms to automatically predict the image quality. The two main ways of measuring that are peak signal to noise ratio and structural similarity index. While assessing image quality, there are two main ways of doing this. The first one that I'll talk about is full reference image quality assessment. With full reference image quality assessment, the assessment is based on referencing the original non-distorted image. So I want to give a brief example to help explain this better. Imagine you're looking at two of the same photos of yourself, with one looking perfect, no changes at all, and the other photo has the brightness that is slightly changed. You can easily tell this because you have the other image to reference. And with this, you can easily see that it is much easier to do full reference IQA. But with no reference image quality assessment, it is the opposite of full reference, where there is no reference to the original image. So in the current example that I already laid out, this is looking at the image that has the brightness slightly changed. But since you can't see the original good image, it's much harder to tell that this image has been altered, and the quality should be lower than expected when looking at the result of the image quality assessment. Using these examples, you can see how full reference image quality assessment is much easier than no reference, and how no reference can be one of the most difficult problems in all of image quality assessment. Even though this research focuses on no reference and full reference image quality assessment, there isn't always a time that you need to use these approaches. For example, some applications like optimizing a video coding systems, no reference image quality assessment is not a feasible approach. So with this knowledge, I will now start talking about the paper and my research project from this paper. So with this paper, they have implemented a deep convolutional neural network with the architecture that is largely inspired by the organization of a person or primate's visual cortex. Once again, we're trying to get a computer, this neural network, to perceive an image like a human would. This is something that is very interesting to me because that is basically what computer vision is all about. And being able to make computers try to see like us humans is the thing that this field is trying to do and will continue to do, but is super complicated and takes a lot of experimentation. Like this paper does, and there have been some good successes from this paper. To make this neural network like a person's visual cortex is comprised of 10 convolutional layers and 5 pooling layers for feature extraction and 2 fully connected layers for regression. I'll now be going into the framework of the two models that the paper has used and will be explaining everything within them. So going into the first deep neural network for full reference image quality assessment, we will start from the left and then go to the right for this framework. You can first see that there are two paths for the reference image and then the distorted image. And they both go into the feature extractor to get features from the images. Pulling these features allows the model to start to learn the difference between these two images. And since we do have these two images, we got to pull features from both so it can compare eventually. You can see that above the feature extractor is a Siamese network which have been used before to learn similarity relations between two inputs. So as you can see with the two paths, this makes it perfect for this model because there are two inputs for these features and it needs to be fused to see what the differences are between the two. Once these features have been extracted, they are ran into a feature fusion step. Once the features have been fused, there needs to be pooling, and then the image quality estimate that comes from the model is the output. Moving on to the deep neural network for no reference image quality assessment. We will do the same thing of starting from the left and moving to the right, but the main difference for this framework, and really the only difference that you can see, is that there is no reference image. There is only one path at the start, and this means that there is no reference path, which also means there is no need for feature fusion from the two separate paths. You only get the features extracted from the image that is distorted and put that eventually into the rest of the model. So there's no comparing and there's no Siamese network. So, of course, a big part of these models is making sure that the data sets that are being used are good and allow these models to be trained and tested correctly. There are three main data sets that have been used for this project, with the first one being the live dataset. This dataset comes from the Laboratory for Image and Video Engineering from the University of Texas at Austin. It has 29 source reference images, which that means 29 images that are the actual image without being distorted. And these 29 images have 5 different types of distortions at different distortion levels. This means that there are a total of 779 quality annotated images, and the ratings in this dataset lie in the range of 0 to 100, where a lower score indicates a better visual image quality. The next dataset that was used in this project is the Tampere Image Database, which contains 25 source images that are distorted by 24 different types of distortion, with also 5 distortion levels for each. This is a total of 3,000 quality annotated images, and the obtained mean score of these images range from 0 to 9, where the higher the number, the best visual quality. This is subjective image quality assessment with people looking at these images and then we getting the mean from all the images. And then the final dataset that was used is the categorical image quality dataset that was created by the Image Coding and Analysis Lab at Oklahoma State University. There are 30 reference images, and the overall database has a total of 866 quality annotated images. This dataset is normalized so that the quality score ranges from 0 to 1, where a lower value indicates a better visual quality. Going on to the results of this project, on the left is the models that the authors created and evaluated for full reference are the Deep Image Quality Measure for FRIQA, and for this table it is DIQAM-FR, and the weighted average deep image quality measure for FRIQA, which are in the full reference section of table 1 is the bottom 2 models. And then if we look for the no reference section of table 1, the two models that are used are the deep image quality measure for no reference IQA and the weighted average deep image quality for no reference IQA. So when you look at the full reference results, you can see that on the live database, the weighted full reference IQA performed extremely well, with the lowest score being 0.970. It had only got beat by another model that score was 0.974. So this is extremely good result for a computer vision model, and as well, the non-weighted but full reference model performs extremely well on the live data set, but slightly worse on the other data set, but still higher than most models that it was compared against. So moving on to the no reference side of table 1, on the project is using more models to compare against the two no reference models that were created from the team. Since no reference is much harder than full reference, the scores are a little lower, however, still very good for no reference. With this, the no reference model that is not weighted before the best overall for this evaluation, with the lowest score only being 0.8335. The weighted no reference model did well on the live database. However, when performing on the TID 2013 database, it performed around 0.77, but only performed worse than one model, and that being the other created no reference model. So if we look at table 2 on the right, which focuses on the performance comparison for different subsets of the TID 2013 database, you can easily tell that the weighted no reference model performs better than every other model it is tested against, and doesn't get lower than a 0.925 on any category. You can also see that there are things that this model does not do well when tested on the live live database in the wild image quality challenge database. The two proposed no reference models perform worse than most of the other models. So there is still room for improvement with these models. So moving on to the discussion and the conclusion from this research, the main thing that sticks out to me is that the author said that better results could be produced by deeper neural networks and more training. Of course, all research comes with time, and of course, more time usually provides better results. And if they had a deeper neural network with more layers, it could get more from the features of these images and produce better results. So a lot of training was used to make sure that the networks that were created were general enough to apply to multiple databases. And with this, it still achieved high scores across different types of distortion. The main thing that is needed to do now is incorporating specific image quality assessment adaptations to the current general architecture that could also lead to more improvements. This paper is a really good starting point for more insight and research into image quality assessments based on data-driven techniques. The authors say that at this point, at the end of the paper, although there are still many obstacles and challenges for purely data-driven approaches, the performance of the presented approach, and given the fact that no domain knowledge is necessary, its relative simplicity suggests that neural networks used for image quality assessment have lots. Sorry about that. And have lots of potential and are here with us to stay. So the main result that stuck with me when reading through this paper is how much data is needed for these models, and how the author stated that getting data is always one of the biggest challenges when creating and testing these models. Like I stated above, with just those three databases, that's about over 5,000 images that have to be quality annotated images to be able to put into the database or into the computer vision model and neural network. And these are all databases that have been made by another team and used for future research across the industry. So even if they did not have this database, it would take them much longer to complete this research, and they would potentially have to find out images and annotate them themselves. So when I ask the question, how have models caught up to the human eye, it really depends on how much data can be acquired. With this, we also have to make sure that all of the data that can be used is good enough quality for the computers to train on, which comes back to these models that were created in the research project. This is a big step that computer vision models have to figure out is how good of a quality of an image is needed so a computer vision model can tell different features and pull different features out of these images. And this is a big step in doing this. If we can find a neural network or some model that can really do this image quality assessment for us, it allows for humans to potentially not have to do these subjective image quality assessments where they're gathering and looking at each specific image and rating that. If that can be done by a computer, that frees up a lot of time to do research on a different thing. So, what are the biggest challenges towards computer vision? When looking into research topics for this semester, I know I want to focus on computer vision. When looking into topics for this specific presentation, when I saw a paper about image quality assessments, this is something that really caught my eye. Learning more about this topic has showed me that this research topic has a lot of future research, and there is a lot that can be applied to this topic. So with the authors talking about there not being enough data when coming to their conclusion for their project, that's why I want to focus on what are the next steps in improving computer vision, particularly with getting more data and data sets. Within, the, within this question comes multiple other questions, but since I have a background in computer vision, this will help me make sure my question isn't too broad. I don't want to focus, I definitely don't want this question to be too broad, but I also don't want it to be too narrow that I'm not finding new ways that this challenge could be applied and what potential solutions could come from this problem. I want to answer some other questions as well, such as are datasets becoming more plentiful with the same image quality? If there is a dataset, let's say, of 100 images and only 30 are good enough quality to be put into a computer vision model, that takes away from the training and testing, as well as someone having to go through these images to make sure that all the other 70 are either up to standard or not. But if you can guarantee that all the images in a dataset have a good image quality, this allows to make sure for faster training and testing. With this, a good question that will help me throughout my data science career is knowing what makes a good computer vision datasets. Most of the datasets that I have been using now in work are datasets that have already been looked at and have already been used before with other computer vision models, so it's safe to assume that these are good datasets. But when there is a time for me to create my own dataset, this will be extremely helpful in knowing what makes a good computer vision dataset. And that isn't just about the images. This is also about looking at these datasets and making sure I have good documentation, good annotation, and making sure it is shared appropriately to help research across the world. This will allow me to know when creating my own datasets for training and testing, but also when looking at datasets over the internet to help find good ones. And then finally, a question that will always be changing is what are the main datasets that computer vision models test on and what makes them unique? Like I said, this is something that will always change, but if I can start to find out what are the key things in these databases, this will allow me to become a better engineer when creating these machine learning models. So here are my references, the first one being the paper I read over and did my research on, and the second one being something that really helped me understand what is subjective image quality assessment. So thank you, and that is all.